My gosh, I had to upload this. All right, so I apparently was not recording. So welcome to our last problem session. And this problem session is going to cover the final exam, basically your final exam content for the entire semester-wide work that we have been doing. And thank you for being great students. So let's dive into what our professor has finally shared with us as in like a problem set that we might have. But there are too many problems out here. So what we are going to do is we are going to group these problems into different chunks or different sectors so that you can focus your energy on those specific sectors. So obviously, since the last homework kind of entails central limit theorem and statistics, you all are going to have problems from central limit theorem and statistics, but it's very, very simple problems, and we are going to learn why they are simple. And then so what you look in front of yourself as your screen in front of you is like an estimation problem. Usually, if you go into any of the machine learning fields or in any of your AI algorithms, they will be working on this specific principle where you have X as certain combination of linear combination of some weights along with some Y variable plus bias called B. And what you are trying to find out is X hat or X cap that is out here, if you see my mouse. And what we are trying to do is we are trying to estimate or we are trying to find out the error of the X hat and the X. And then what we are trying to find out from that error is, okay, now that we have an error, how to minimize that error. So we are going to find the optimal A and the optimal B that can be put back to the equation so that at each gradual steps, we are going to bring X and X hat much more closer to X. So this is your basic machine learning structure that you have. For those of you who are going to take up 4330, we are going to have something called DPCM, which works on the basic feedback principle. You know, if you have taken control system classes, your feedback, what it tends to do is to minimize the error, you know. So this is some kind of minimization of the error. And this is unfortunately not a specific problem that we have done in the homeworks. This is a part where you have to actually look into the book, and probably professor has covered this several times, but at the end of the problem session, we are going to come back to this problem, to that specific area of the book, if I recall properly. And then if I don't recall, I'll forward you a document, a 3-page document where we have like derived the entire thing, and then we can share that as well. So it's a very easy problem again. This might not be the exact structure of the problem, but usually A is called the weights and B is called the bias in machine learning terms. That's why it's one of professor's favorite problem. So you might have something like that as well. So 3 problems from statistics will be definitely there. We are going to solve those 3 problems. I'm going to turn off the video when I switch to the presentation mode because of the bandwidth that we have. So this is one of the problems. This is the 4th problem that you have. Now, professor has also solved Jacobian. I'm not too comfortable in giving Jacobian problems. It might be there. Okay, I'm just giving you a hint. Maybe a 5-point problem could be there. I don't know. But I will be sharing materials. We might not do Jacobian problems right now because it's too late for us to, you know, do any homeworks and stuff. So I'll let you know about that. It's not going to be a complicated one. But the basic 3 statistics problems, 1 central limit theorem, 4. This one, the estimation problem will be 5. And there will be another problem from the chapter 5 kind of, where probably you will be told to find out the covariance and whether the covariance, if it has like what kind of interpretation can you do from the covariance result? Is it a 0 or is it does it have a mathematical value? Is X and Y independent? So these kind of problems will also or might also be there. So we are going to cover those problems as well. So that's your basic thing. The problems that you see 5.8 onwards, basically 5.8 to 5.31 is your homework 5, I guess. And then after that, we have homework 6. So focus more on homework 6 and 7. Homework 5 is also important in terms of your mixed random variables that you have learned. But usually the focus might not be on, you know, trying to find out the marginal values and stuff like that, because you've already done that. It's much more on correlation, covariance, expected value. and those kinds of problems. Okay, so I'm going to turn my video off because I'm going to start sharing my screen. Okay, so again, welcome to the last problem session. And if you have any questions after the problem session, please let me know. I'll be more than happy to help you. So your exam timing and everything is already given. I will also send you a kind of bigger note on any kinds of instruction, the timing, the room, everything else. Probably by Sunday. So you don't have to worry about even if you don't know when and where. All right, so we are going to start with central limit theorem, and central limit theorem, please, please, please remember this. Even if you forget the entire probability lecture, everything, please remember central limit theorem. This is very important and it's very simple. Okay, we are going to learn why. Okay, so don't worry about it. I'm not taking in presentation mode unless I'm working any problems out. So what happens in central limit theorem is that, you know how we take an experiment and we keep repeating it for n number of times, right? And that n, if that n is pretty large, then what happens is that, let's say, for example, you have a sum of large number of values. Okay, so you have found out like 6,000 values and then you have summed it up. And now you're like, let me actually get a nice value. Let me normalize it. So normalization is a technique, again, like very common to machine learning processes as well, if you are interested in those kind of stuff. But here in front of you in the book itself, I've taken this from your book. So what we do is Sn minus n mu. So what is n? And first of all, what is Sn? Sn is the sum of the n number of terms. Okay. So if you subtract that from n times the mean is basically the mean of the distribution that you have out here at hand. So again, even if you know it, just consider this to be the sample mean right now. Okay, I know this is like a little bit difficult for us. And for those of you who will be studying random processes, the sample mean and the absolute mean might be different. So just let's take this for simplified case as the sample mean. So if n times mu and then divided by the standard deviation, so this is some kind of like standardization or normalization that you are doing. Now, if you do that, you'll find a number called Zn. Now, the Zn is not any ordinary number. The Zn has to be a zero mean unit variance random variable. Okay. Now, if you take that Zn, and that Zn tends to be a zero mean unit variance random variable due to the operations that we have done on it, done on Sn. So Sn has now been transformed into Zn. Now, if you are taking the CDF, remember, if you have like P, x less than small x, it's like the CDF kind of structure, right? So n tends to infinity is nothing but just signifying that this n is like a very large number. If you take the CDF, it comes out to be in some format of a Gaussian, which is very surprising because this sample mean could be any sample mean, right? It could be a binomial, it could be a Poisson, it could be anything on the entire world. It could be a gamma random variable, a chi-square, anything, right? So this any random variable, if the sum is if the n is very, very large, and then the sum might not be large, but if the n is very, very large, then if you are trying to actually find out the CDF of this kind of structure, it tends to be a Gaussian. So it's a very interesting kind of observations that we have, that if you keep on adding n numbers, right? And if you keep on increasing the distribution, the more you kind of increase the distribution and the more you tend to normalize this stuff, and then you try to find out the CDF of this kind of structure, the more it will actually be a nice, a bell-shaped curve. Okay. Now, there is a condition, however, that this is identically and independent and identically distributed. Now, this term is very important, not for you specifically. You just have to know that this is like equally distributed data, which means that I don't have like, how in a big jar, if you have like some kind of marbles distributed, these marbles are distributed uniformly across the entire jar. Like not like in clusters, you have like 10 marbles in one cluster and then 5 or 2 sparsely distributed. No, this is uniformly distributed. So then it will follow this. But there was another case in which Dr. D and I kind of found out that it might not be essential for this distribution to be IID, but then that's not important again. Just remember that this is an IID distribution, and for your exam sake, this is an IID distribution. So you don't have to actually worry about this, okay? So having said this, why is this important is because usually again, so if you take a problem, let's see, let's go to our problem sets. So if you take any problems, you don't know why is it powerful. You don't know the type of distribution that you have at hand, but then you know if you have enough of it, you can actually approximate it to be a Gaussian. That is why Gaussian random variable is very, very important. I mean, at this point, I can actually turn on my video. You have like, usually again, when you actually consider noise, okay? So when you have noise data, you usually would take an additive white Gaussian noise. Again, for those of you who will be taking up telecom, or even if you don't take telecom up, any kind of communication noise structure, even if you are into power or controls or anything, most of the signals, which is termed as noise, they can be actually approximated very well as additive white Gaussian noise, because it's enough in number. And then if you keep on adding these, it will actually take a bell-shaped curve. That is why it's so essential for us to know why Gaussian is so important, because of central limit theorem, because if you have enough of these numbers, you can actually have a bell-shaped curve for that. So you might not, again, have the entire picture of why it's important, but know this, that if you have enough of something, you can actually, by the central limit theorem, approximate it to be Gaussian. And we'll see why it's important. So let's go to solve problems first. And these problems are already there as part of your to actually go about it. Okay. So because I get the question of, okay, we know everything, that's great, but then how to solve the problems, right? So here we have the problem one. This is very, very easy problems, provided you know what to do, right? That's always the case. We don't know what to do. So that's not that's not a surprise. Right, so let's see if I can actually draw with my crooked handwriting and hope you understand. So the first step for you let me use my keyboard. Okay, the first step for you is to understand that, there you are, is that Z is basically a random variable. Okay. Now, if I would have given you just an equation that Z is equal to X plus Y, you wouldn't make anything out of it. It's just a linear combination of numbers, and this is just an equation, right? But then I have told you that this is, yeah, this is not a very good representation. So this is a different number. So this Z and this Z is different. Okay, guys. I mean, this is just how the problem has been stated. So this Z is different than this Z. Okay. So don't get confused on that. So X, Y, and Z are basically, they are not just any numbers. They are given out to be, first of all, zero mean. Okay. Now, what does zero mean mean? Okay. First of all, we'll find out. Okay. So they are, first of all, zero mean, unit variance. So these things have a meaning, right? I mean, most of you know, but most of you have again gone wrong with your problems in your midterm exam. So I'm kind of specifying them. So zero mean and unit variance, and nothing else has been told about that. Okay, so just this, no Gaussian, no nothing. It's just that it's zero mean and it's unit variance. Okay, they are just random variables. Okay, just random variables. Now, don't assume that you have zero mean and unit variance means immediately you're going to conclude that, oh, it must be equal to Gaussian. No, we are not given that. Okay, no, this is not Gaussian. So this is just zero mean, unit variance, some random variable. Okay, so that's the first mistake that students make. So don't jump to conclusions. All right, I keep losing my mouse. Okay, now you have the covariances just given, so I'm not writing it out and wasting time out here. So all the covariances, basically, I mean, if you want, you can write it out in your exam, because if it helps you in that case. So, okay, then what is the expected value? So when I say expected value of Z, you have to understand that I'm talking about the mean. Again, like in the beginning, I have told you that please consider the sample mean and the actual mean as the same. So this is the mean, okay? This is the mean, Now, what is it equal to, right? So we know x, y, and z. Now we don't know this z, right? So we are trying to find out the mean of that z. So it turns out that the mean of that z is basically, now what we can do is basically we can only just substitute this z. So what is that z equal to? That z is equal to x plus y plus z, right? That's what we know. Now, from that, we can actually try and find out that, okay, these means are exceptionally known to us. So we know the mean of x, we know the mean of y, we know the mean of z, and they are all 0. Okay, so basically, this entire thing is 0. Why? Because, well, that's given to us. This is 0 mean. Each of them are 0 mean. This is 0 mean, this is 0 mean, this is 0 mean. So this should not be like too hard for us to find out. Now, next term is basically your variance, right? So your var, now these formula will always be given at the back of your book. Now, you should not expect me to give you this, because if I literally give you, this might be given as, you know, at the back of your book, this might be, I'm just saying it to you. Okay. And now if I give you this entire thing, then you have nothing to, you know, solve, right? I mean, yeah. So this might be given to you at the back of your chapter, like x of fx of x dx. Okay. So I might be giving you this kind of formula at the back. Okay. Don't get scared. It's just a mean. Okay. This is just a mean. So don't worry about it. So the mean is basically the mean of, first, just substitute what you have. What you have is the z, right? So z, write the z out. Now what do you know about x, y, and z? They are 0 mean. So the entire thing is 0, right? So now we have the variance, right? Oh, no, that's the wrong thing. Sorry. All right. So now the variance of z, okay? So what is the variance? Now we also know that this is unit variance. So, okay, great. But that's not the variance formula, right? There is a formula for the variance which involves the covariance as well. So now what we are going to do is, where's my mouse? I keep losing my mouse. Okay, there you are. Okay, so the variance is basically the var of x, which is great, plus the var of y, plus. Now this formula will also, if this specific problem comes in, this formula will also be given to you. But I need you to understand why this is common sense. Okay. Minus, I'm so sorry. We are not sorry, plus 2 covariance of because they are correlated. These numbers are all correlated, right? So we'll talk about that. Why is this formula like this? I mean, if you understand it, that's great. But then if you don't, actually, these are numbers. So let's put it that way. So we have done x, y, y, z, and then 2 of, so this formula is also given at the back of your book. I mean, not the back of your book. I mean, in your book will be given at the back of your exam. Wait, I have done x, y. I think y, z is left. Okay, yeah. So again, what we are trying to find out is the variance, right? So it's obvious that we have to add the variance of the 3 variables, but then they are also having covariance. That means they are correlated. The x and the y have a correlation between them. The y and the z have a correlation between them. The x and the z also has a correlation between them. That means this random variable and this random variable, if you find the distribution of these two, they have a joint distribution somewhere, right? So you have to consider that joint distribution. For those of you who are interested, this formula can be actually derived. Okay, so just for the sake of your exam, this formula will be given at the back of your exam. All you need to do is to just find out the value of this, whatever the value is. I'm not going to find that out for you. Now, repeat the part, assuming that x, y, and z are uncorrelated. Well, if x, y, and z are uncorrelated, then basically your mean does not change. Your mean still remains 0. The variance will be 1 plus 1 plus 1, 3. Because uncorrelated means these values are basically 0, right? So that's your part B. So part B is the var of mean stays the same. The var of z is basically 3. Basically, the correlation between these two values are basically 0. So the variance not only has the variance information, it also has the covariance or correlation information between any of the two variables that are, or any of the three variables, like two variables, and then again two variables correlated with each other. So that's all you need to know from this problem. So if you move on, now these type of problems are not going to be of high magnitude. Like this might be having like a 5 points. If it's at all there for the exam, this will be like a 5 points or maybe 6, 7 points. Because it's pretty straightforward, It's just straight use of the formula. Okay. Now this problem is very important. Okay. Now this problem, you already know how to solve this problem. In both parts, I'll show you, I can prove you that you already know how to solve this problem. But why are we solving it in this way is important, okay? Now, or rather, why is it a central limit theorem problem is also important. Now, this problem could have been given it to you in the, maybe in the first term exam. If I would have given you the problem, or maybe in the midterm, you would have actually done it exactly the same way using the Gaussian concepts that we have, the Q table and the characteristic function. Whatever is given out here, you have already done that. But why is it a central limit theorem problem then, right? That is important for us to understand. So let's read the problem first, okay? A fair coin is tossed 100 times. So 100 is like, kind of like a big number. I mean, I wouldn't say very big, but usually, central limit theorem, according to my observations, again, it usually works very well above 30 or 35 or 40 observations. It kind of gives you tends to give you, or starts giving you, a good Gaussian, kind of characteristic. So 100 is kind of very standard value for that. So the better, if you have 1,000 out here, it will be better. But I mean, that's not the part of the problem. It's 100 times, so that's n is 100. So now imagine, forget about the fact that this is a central limit theorem problem, okay? A fair coin is getting tossed 100 times, right? So we know that this is a Bernoulli trial, so we are going to put this in a binomial distribution. So now estimate the probability that the number of head is between 40 and 60. Now you have done this type of problems already in Gaussian, right? That 40 and 60 kind of thing. Estimate the probability that this is between 50 and 55. So this, I think the exact limits were given to you in the midterm as well. This exact 40 and 60, or maybe 50 and 55, this may be a very familiar limits for you. But then you might ask me, well, how do I even go about doing this problem? Because I know that this is a binomial distribution. How do I estimate the probability between these two numbers? This is a binomial problem. I mean, how do I put it in Gaussian? There's no mention of Gaussian random variable anyway. Well, the surprising thing is that what we are trying to do is we are trying to solve this in terms of central limit theorem. And as according to the central limit theorem, first of all, our number n is high. So even if you go about solving it with the intention that you have it to be a binomial random variable, then you have n as 50, right? So because it's NP, this formula will again be given at the back of your exam. So the expected value or the mean is NP, and the variance is NP1 minus P. So this will be given. So you find that out. Great. What do you do with it? So now, according to the central limit theorem, since you have the probability of the number of heads, and we are trying to find that in some estimate, you can actually estimate this binomial random variable as a Gaussian random variable, okay? And then try to actually put this in a Gaussian problem, because these two are not related. Guys, like if n was 10, you can still do it. I mean, there are distributions in which you can actually put very low number of times and then also find out that variable. But the point of central limit theorem is n tends to infinity, right? So if you have that concept in mind, a binomial random variable can also be approximated into Gaussian, and that is why you have this Gaussian. Now, I'm not explaining this exactly as I have done for the midterm, but you know that this formula again will also be given at the back of your exam. I'm not going to give you the exact numbers. I'll put A and B out here. So A and B, how to use it, you already know. This is just 40. 40 means the lower limit, and then 60 is the upper limit. Where do you get the number 50 out here? 50 is basically your mean. Where do you get the number 25? 25 is basically your variance. Don't forget to take the square root of your variance. Please, you have gone wrong. Some of you have gone wrong with this concept at your exam, the midterm. Please don't do that, because that actually ends up in a wrong calculation and I have to take out points for that. Okay. So basically A and B. A is your this limit, B is your this limit, A is here, B is here. So you find out -2 and 2. Hold. This is not your Q value. Okay. This is not your Q value. B minus A. But what is it? Phi. Phi, remember phi from your old classes, old exams? So phi of 2 minus phi of -2. Then you change it to Q. Step 1. Remember, as we studied step 1, step 2, step 3. So this is your step 1. Then you do step 2. Then you do step 3, which is your characteristic function phi. Step 4 is your Q. These steps will not be given to you at the back of your exam. You have to remember these steps. So phi is already there, and Q 1 minus that number. So then you find out the values, and then Q table will also be given. So Q of 2, you'll be able to find out that value, put it in that value, and then find the final results. So similarly, for the next set of values, you can also do the same thing. And similarly, if n is very large, it's just going to be also approximation of the binomial by the Gaussian. You can also find out the same thing for these two limits. So it's stuff that you already know. So please be careful that you already have done these things. So that is why the final exam is much more, like I kind of promised you all that the final exam is much more easier than your midterm. This is why it's easier, because you have already done this. Okay, you already know the binomial distribution. You already know the Gaussian, how to solve it, how to look up the table. We have gone through this phi, how to convert phi to Q, and then how to look up the Q tables and put in the values. That's all you have to do. Okay, the same thing, it keeps repeating like 100,000 times. It's same thing. Where people have gone wrong in the problem in the midterm is, first, you don't know what the Gaussian formula looks like. Okay, so that will be given at the back of your exam. All you need to do is to flip at the back of your exam, see the formula and put it. Now, the second part was that 40 and 60, y'all don't know what to do with the number. Y'all did not know how to write this P of 40 less than n less than 60. Why is this? Because we are trying to find out the estimation of the probability between 40 and 60. So the random variable that we have, we are trying to find, okay, what are the chances? What is the probability that the distribution will be between 40 and 60? That is what we are trying to find out. And we find out, okay, it's 95% chances that the n that we are trying to find out is between 40 and 60. Similarly, 50 and 55 is like only 44% chance. Okay, that's what the number means though. So please don't forget to do step 1, step 2, step 3, step 4, look up the value, step 5. Okay. So if you are confused about this part, come and talk to me. Okay. You still can Teams call me and I'll explain you the same things. So this problem might be important for you, for your exams perspective. Okay, let's move on. Oh, sorry. Can I move on? Why can't I go to the next slide? Let me see. Let me take a pen. Okay. Now we move on to statistics. Okay. So let me see. Okay, hang on. Anyway, I mean, I was trying to show you the book, but there is no need for that. Or maybe I will actually. Let's see. So for statistics, you have something called, nope, that's not what I wanted to show you. Let's see. Okay, so this is central limit theorem. Central limit theorem is obviously important. So what we are actually going to concentrate on in the entire chapter 8, you have lots of different topics of interest. Maximum likelihood estimation could be an interesting topic for us. Hypothesis testing could be an interesting topic, but we usually assign problems from the confidence intervals because you need to know how much of a confidence intervals or how to solve the confidence intervals. It's very powerful method again. Now, given that this is Gaussian. Now, students come back and tell me that what if it's non-Gaussian? Well, it can be non-Gaussian as well, and you can solve the problem as well. Usually in the exams, it's taken that it's Gaussian. So don't come up and tell me that, but I had pretended that this is non-Gaussian, so I have applied this formula. No, it will be given to you that the problems that you have, they are Gaussian in nature, okay? So don't cry on that one. Now let's see if I have that table somewhere. So again, like these are the different cases that you have. So the first case is if you have followed the lecture, you know that if it's an unknown mean and unknown distribution, unknown mean and known variance. So this is the keyword. If it's known variance, it's a Z distribution. If you have variance unknown, then it's a T distribution. And if you have like some of the wordings of these problems are actually important, and that's where people actually go wrong. And then if you have, again, non-Gaussian, we are not interested in that, but you can also solve problems with that as well. I mean, not saying that they are not important from your exam perspective. So this is like a typical non-Gaussian. You can actually solve it with chi-square. Chi-square is actually an interesting so summary of the confidence intervals for random Gaussian variables. You have all your summaries, and this is your chi-square. So chi-square is actually interesting. So when you have, so the basic question that come up to me all the time is that how do we know, right? So how do we know which intervals to use, and how do we even know what to do? So in that case, actually what we have come up with is a table. Now this table is also from your book. Now this table tells you, and this table will be there in the exam, okay? So that is why I'm kind of like trying to explain you in the terms of the table. Now this table, like you see out here, the critical values, I have just shown one table just for the time's sake. But these kind of tables are basically one for Z distribution, one for T distribution, one for chi-square distribution. Now, you have to understand when to use what, because I'm not going to give you, okay, statistics, problem 1, Z distribution. No, I'm not going to give you that. You have to infer that. Now, how do you infer? Like we saw in the book, we have random variable, which is having a known mean. My bad. A known variance will always have a Z distribution. Now, be very careful. This is Z of alpha by 2. Okay, you see this value, Z of alpha by 2. This is T of alpha by 2. This is chi of alpha by 2, actually chi-square alpha by 2. And then this is chi-square 1 minus alpha by 2. These values are important because what you will be finding out is the value of alpha. Then from there, you have to find out the value of alpha by 2. Okay, we are going to do problems on that. We are going to find out. But this is your basic structure. And then from there, you're going to look up table. What are these tables that I'm referring to? These are the tables that I'm referring to. Okay, so for example, if you have an alpha of 0.05, okay. So now what is alpha by 2, right? So that is basically 0.05 divided by 2, whatever the value is, okay? 0.025, right? So then now you take this value and you search it in this table, okay? Is this the value? Yeah, this is the value. So then you look up this number first, okay? This is the number that you look up. And what is the value that you take? This is the value that you take. So then if it's, I'm assuming that this is Z distribution. So then Z of alpha, So what is the value of Z of alpha right now? This is 1.96. Okay, so let me write that down. So that's how you look up the table though, basically. It's the same as looking up your Q table. As you find out the Q table, oh, sorry, that's not 1.92, 1.96. So basically you understand the point, right? Like, it's the same as looking up your Q table. So now people don't usually go wrong in looking up the table. People go wrong in this all the time. You always take alpha, you straightway say, oh, okay, 0.05, it's 1.64. No, that's wrong. Because both the Z distribution is out here and then out here as well, right? So both of your distributions are there. You have to take 1/2 of the distribution. We are only looking at 1/2 of this distribution. That is why it's alpha by 2, right? So 1/2 of the distribution is basically alpha by 2. And then you have to, whatever alpha you find out, however you find it out, you have to divide that by 2. And then you have to take on T table or chi table or Z table. These are the 3 types of problems that you will get. Z, T, chi. All the 3 problems will be there on your exam. Okay. And we are not going to tell you which is which. So if it's a known variance, it's always Z distribution. If it's an, usually if the variance is unknown, it's always a T distribution. And for chi distribution, we'll see a specific type of language being said. Then you would know that it's a chi distribution. Now, interestingly, T distribution also has another trick that you will that I'll tell you when we come to that problem. So the very obvious problem first to solve is the Z distribution. It's so obvious that I haven't solved it for you. It's again from your solutions that you have. So what is this problem saying anyway, right? So first read the problem. I'm not going to mention statistics on the top, right? This is just going to be a random problem for you. How do you know that this is a statistics problem? Or how do you know that I am trying to like make use of the confidence interval? Where is that term? Well, the term is in the question. So if you see the word confidence interval, you would know that this is first of all a statistics problem. Okay. And second of all, you have to look up this table that we have out here and find out whether it's a known variance, unknown variance, or what is the wording of the problem. Okay. So random variable where mu is unknown might or might not be always true. Chi-square is used at a typical language lookup. I'll tell you about that. So first is basically your problem. So let's read the problem. The voltage measurement consists of, excuse me, hang on. Sorry about that. All right, the voltage, okay, let's read it again. The voltage measurement consists of sum of a constant known voltage, unknown voltage, and a Gaussian, okay, Gaussian distributed noise voltage, 0 mean variance is given. Now, usually, again, when students read the problem, it's an exam hall, it's a very tense moment, this is your final exam. People are like, oh, okay, let me read it. A voltage measurement consists of sum of unknown voltage. This has to be, no, read the entire problem. Unknown does not signify anything. This is not signifying unknown mean. This is not signifying unknown anything. Read the entire problem. Yes, the problem has this as a specific wording. What is the wording? Gaussian distributed. Okay, go back to your table, immediately eliminate non-Gaussian. Non-Gaussian is eliminated. Okay, now I have to see this one, and this one is a possibility. Okay, let's read. 30 independent measurements are made. But then when you stop reading, you'll realize that your mean is given and your variance is also given. Okay, let's get back to the table. Not sure. Next, Gaussian random variable unknown. No, our mean is given. Our variance is also given. Let's try this one. Gaussian random variable. Okay, this matches up because my variance is given. Then you select this confidence interval formula. This is the CI interval formula. Okay, this is not any other formula. This is the CI. Okay, so then that is why in the CI formula you use this one, the Z distribution. So why is this important? Like, why is it important for you to first come to the conclusion that this is Z distribution? even before starting the problem, you are kind of trying to infer that this is Z distribution. Why? Because when you look up the table, eventually when you do your entire calculations, when you look up the table, it's either T or Z or chi, right? That is why it's important. Even before you actually end up with the CI formula, you will actually find out the Z of alpha by 2 or T of alpha by 2 or chi of alpha by 2, right? You have to find out this before even you start the problems of finding the CI. So that is why it's important. So first identify which type of distribution. Let me write this down. Let me take, can I take a different color? Interesting. So step 1 is identify distribution. Okay, I'm just writing in this in short. STR. So identifying the distribution is the step 1. Now step 2 is to finding out the alpha. So that we are going to do now. So then, okay, great. Now we have found out the distribution. Let's go ahead and then try and solve the problem. What is the problem? The problem is that we have to find out the 95% confidence interval. What does that even mean? So let's go step by step. So every problem of probability, first is the data recording step. All of your problems will be recording the data first. Once you have this step done, you will actually feel much more confident in starting the problem. And then obviously you will also get partial credits. That's not the point. You're not here to get the partial credit. You're here to get the full credit. So sample mean is 100 microvolts. Okay, that's kind of relatively very small. But anyway, the sample mean is given to us because there are 30 independent measurements. So N is given. And then there are sample mean also given. Sample mean is basically your 100 pico micro, whatever it is. So then you have a known variance. So that's Z distribution. So you can either write Z distribution as your first step, or you can write, okay, since the variance is known, we are concluding that this is Z distribution. Just write one word or one line on it so that our professor understands that, okay, so this guy knows that this is a Z distribution. Great. 95% confidence interval means 1 minus, so whatever percentage you have, okay, you're trying to convert 95%. 95% is there. You convert that to 0.95. Okay. So you're confident 95% of the time, right? And you're trying to find out that interval. So what is that interval? This is 0.025. This is 0.025. This is the 95% confidence interval. So this is your alpha, right? This is one of your alpha, and this is the second of your alpha. These are divided in two parts. So that is why this 0.05 is divided into two tails. One tail is out here, one tail is out here. Like both. I mean, I know that you cannot see my pointer. So one tail is out here, one tail is out here. That is why we have 0.05 divided by 2. Okay. So alpha will come out from the confidence interval value that is given out here. So usually in machine learning as well, we tend to like find out, I mean, ideally we could do 99%, but I mean, you know, like 99 is like it's actually not impractical in healthcare solutions, but well, usually 95 is a good interval to find out, you know. So it's a standard kind of confidence interval. So 95 you'll see repeated in a lot of problems a lot of times in your life as well. So that is why this 0.05, and then everybody kind of knows if it's a known mean, known distribution of a known variance, then we have Z, and then if it's Z, if Z 0.02. So this is almost like known by everybody. It's so popular. Anyway, you have to solve it out. You cannot say that, oh, since I know this, no, you cannot do that. So again, I have seen a lot of people. It's very hard for me, since it's a relatively big class, to monitor every one of you. Okay, let's put it that way. So for us to make the professor know that you know the steps. Now, some people, y'all are very good batch. Okay, we know that you know most of the problems, you know most of the things, but do write it down, because otherwise we'll think that, okay, is this, did she or he try some other techniques, or do they exactly know the topics? Okay, so write it down. It helps us it helps us in understanding whether you have understood it or not, or you have understood it properly or not. So write down. So I have seen, like, most of the people, you have this entire problem, right? So for most of the cases, you have this entire problem. I have a blank sheet, and then only the answers written. Like, only maybe this will be written as the first step, and then CI will be written as the second step. I don't know what you have done to find out Z of alpha. Maybe they have done it in somewhere rough or something, but show us the work. Even if it's dirty, even if it's like scribbling all over the pages, we want you to scribble all over the pages and actually work it out on your own. Don't worry about neatness. You're here to work out and understand what you are doing. Okay, just letting you know. Okay, this is not an important part of the problem. Anyway, so as you have found out, like, I have this pointer, I cannot go. So as you have found out from the table, if you have 0.05, you divide it by 2, because you are finding out for one specific tail, and then you look up Z of alpha is now 0.025. So the Z of alpha, according to that, is 1.96. So that is what you write. Okay. Now, once you complete that, you move on to this step. Okay. So then identify the distribution is your first step. And then the second step of this problem is to calculate maybe let's calculate alpha. Okay, and then you calculate alpha by 2, and then you put it into the distribution, and then you look up. Okay, lookup is the next step. So calculate alpha by 2 and look up whichever table you have to look up. And then the third step is the CI. So CI, where do you take the CI from? Let's actually erase these parts out so that you can see it clearly. So CI is these parts. Okay. So CI will be given to you. So first step of the CI is xn minus Z of alpha by 2 sigma divided by square root of n. This is one interval. This is the second interval. One interval, second interval. What do you need to do? What you need to do is basically find out the values. You have xn. Why? Why do you have xn? You already have the sample mean, right? It's 100. So 100 minus 1.96 is the value that you found out for Z distribution. Where do you get this 10? Well, its zero mean and variance is 10, right? So divided by 30. Where do you get the 30? N is equal to 30. Why? 30 independent measurements are made. You're not given like N is equal to 30. There are specific types of number of measurements that are getting made. So that N will be 30. That is why it's square root of 30. And then you just find out the interval, and that's your full answer. So this is not difficult. This might be a little bit tricky, because depending on the distribution, now if I would have approximated this by t distribution, my values would have been way off. So that is why it's a little bit tricky. But the working out of the problem is pretty simple. Like, it's just remembering that, okay, step 1 is this, step 2 is this, step 3 is this. Again, it's the same as how you work out this problem. So for central limit theorem, just going back and trying to show you, this is your step 1, right? So step 1 is finding out what type of mean and variance you have. Step 2 is identifying the central limit theorem formula. Once you do that, step 3 is putting it into characteristic equation. Step 4 is Q value, and then looking up the Q value. So from phi to Q, you have a formula, right? You cannot do it without the formula. You have to convert that from phi to Q. And then once you convert it, you put the values of the Q, and then you find out the final answer. So if you don't follow these steps, your problem will be wrong. That's all. Let's see what else we have. Okay, so well, this is a second type of problem. I'm not going to solve the part A because it's kind of obvious, but we are going to go through it. So the lifetime of 225 bulbs is measured, and the sample mean and sample variances are found to be. So sample mean and sample variances are already given to us. So let's see. Sample mean, put the Sample mean is there, sample variance is there. Find the 95% confidence interval. That means it's immediately Z. You don't have to even think about it. The sample variance is already given. So the first part is basically the same thing that we have done in the previous problem. Okay, so I'm not discussing the same things again. But again, it's 95% confidence interval is like a common number. So you all automatically might think that, oh, let me immediately write Z of alpha by 2 is equal to 1.96. You know, now you will get the full points or you might not, because I don't know how professor will grade your exam, but your professor might give you 2 question marks out here saying that where did you find this value out? Oh, no, professor, I know that if it's 95, no, nothing is implied. Find out the alpha, find out alpha by 2, just the steps that we have done. Even if you know the value, identify the distribution, calculate the alpha by 2, look it up. And then even if you know everything, put down those steps so that, again, we don't know how you know it, right? So put down those steps. All right. Next, this is just putting down the values and finding out the interval. Now, this might be a large number or a small number, so don't worry about that. But it will kind of, it's kind of interesting for you to observe that it can be like 98.9. Now look at the mean. This is a zero mean kind of situation that is going on. So these are like numbers, but this is almost having like a 223 mean, but your numbers are not varying too much. So these are some interesting observations that you have. Like if your variance is quite kind of, 225 value is like very closer to 223, right? So the sample mean is very close to the actual number of distributions. That is why your interval is almost very close. Just small like observations. These are not important, but for your deeper understanding. Anyway, so what about part B though? Find a 95% confidence interval for variance of lifetime. What does this word mean though? For the variance. So if you go back to your book, you will actually see that summary of confidence interval for Gaussian random variables. This is an important thing, okay? So what does this mean for Gaussian random variable? So when you use this word, again, I can describe you all the derivations and every other things that are there. But again, for the exam shortcut, you can actually see that for the Gaussian random variable is almost like chi-square, okay? So whenever you see this language getting used, you can actually, you can actually use this shortcut, okay? So then for the variance of the lifetime means that it's 95% CI, but the CI values are going to be chi. Okay, so let's see what chi actually looks like. Well, it's n minus 1. We already have n. Sigma squared, well, that's variance, so that's fine. Now chi of alpha by 2. So you should have already found alpha by now. Alpha by 2 is again just alpha then divide by 2. But then here is 1 minus alpha. Please remember this. Again, students go wrong with this. So please don't forget that. So this is 1 minus alpha by 2 and this is alpha by 2. Now, here is an important point though. If we give you values that are not in this specific lookup, table. So if you see the lookup table and the degrees of freedom that you have for this specific value of 100, you will see that it's only till 100, right? Now, what you have found out is basically some value of n minus 1 is 224, right? So for 0.025, so alpha by 2 is 0.025, right? And comma 224, you don't have anything out here, right? Like, what are you going to find out? Like, this is n and alpha, right? So n and alpha, this range is not suited for that. So then what do you do? Right? What do you do? So you have n out here. You have the n value out here. So how do you read this table again? So n is these. N is equal to 1, n is equal to 6, n is equal to 14, all the way down to n is equal to 100, right? These are the n. And what is your alpha values? These are your alpha values. Alpha, this is alpha, this is alpha. Again, this is an alpha. So your vertical is basically, no, this is your horizontal, right? So the horizontal is basically alpha and the vertical is basically your n. So again, why is this important for us? Because the formula states that this is alpha by 2 and this is n minus 1. Very, very, very important, n minus 1, and this is not n, okay? Not n. Nope. So again, coming back, if you don't have this large n, we will be giving these values to you explicitly, okay? You don't have to panic. This will be given to you in the problem. Take chi-squared as this and this for problem so and so. If it is a value that is not given in your table, it will be given to you out here, okay? In the maybe at the back of the exam or maybe along with the problem. So don't panic if you get a value which is not there in the table. Look up the table. If you don't find the value in the table, so how do you look up the table? Okay, first of all, let's go step by step. You have identified that this is chi-squared. First step, chi. Okay, second step is that, okay, you have to find out the alpha, but you already have the alpha out here, which is like from this part, you already have alpha is like 0.025. So you have that. So you have alpha, oops, as 0.025. Again, if you don't understand that, go back to problem 1 that we have solved out here, and you will be finding why it is 0.025. So we have 0.025 and n as given as 224, right? So then you look up your table. Okay, let's go to the table. Okay, 0.025 is found out. Okay, now n, right? So you're looking at all the values and then you're trying to find out n. Oh, it ends at 100. Then you ask, okay, where can you find this type of value? Is it given anywhere in the exam? Then you look up, oh, okay, maybe it's given at the back of my exam. Let me look at the back of my exam, more examples, more stuff, and then you'll find out this value is given. If by any chance I miss it, I will be writing it on the board. If by any chance, okay? So all possibilities are like explained to you right now. Now, nothing left right now much. It's just that you have to put in the values in the intervals. Don't make a mistake in putting in the values. If you do, well, I really cannot do much about that. But anyway, the same thing is explained out here. It's like one tail. So it's like 1 minus 0.95 divided by 2 is 0.025. So the alpha is 0.025. And then just write the values out here. And that's all. Like punch the numbers in your calculator. Please punch it properly. And then sometimes students leave things in fraction. It's okay when you do leave things in fraction in terms of when you were doing your first or second homeworks. Then, you know, when you have like you're repeating an experiment, you're rolling a die kind of 1 by 6 and 2 by 6, these values are okay. But when you move on to your much more in-depth statistics or your central limit theorem, we do prefer decimal values. But if it's okay if you put it in fractions, but just letting you know, like, you know, it would be nice if you put it in decimal. Again, if you put it in fractions, no problem. Just something to be, you know, since it's a final exam, you should be learning most of the coursework. So just letting you know. Okay. Oops, sorry. All right. Now, okay. This one we can actually solve together with my horrible mouse movements and handwriting. I hope you understand what I'm doing. So, okay. Now I've given you a hint, but I have said like at the beginning of this problem session that there is another very beautiful way of identifying t-distribution. Now, obviously, you have to actually read the problem first. There is no doubts about that. But then, you know how you have these little tricks and tips of identifying it's a binomial or it's a Poisson's or it's any other type of random variable. This is also a trick. So if I read the problem, I identify a couple of things. Okay. First, it's Gaussian. That's very important for us, you know. Then we have unknown mean and unknown variance. So unknown variance is important to us. Okay. So we have a Gaussian unknown variance. Okay. So let's go back. Gaussian unknown variance. So first thing, Gaussian known variance, eliminate. Non-Gaussian, eliminate. Gaussian unknown variance. So this is a t-distribution. All right then. So we now know that this is a t-distribution. So first is t-distribution. First you know that this is t. Okay. Now, a set of 10 independent measurements of X yields a sample mean. So your sample mean is given and sample variance is also given. Now you're told 90, 95 and all these other values, right? So usually again, 99 is, well, sometimes might be required for certain perspectives and stuff like that. But then, yeah, I mean, 99 is also like sometimes required. So 95 is 90 and 95 is like most common. Now, if you observe that a set of 10 measurements is kind of a less number. Usually you see like, oh, set of 100 measurements are taken, or a set of like 500 measurements are taken, right? So these are the numbers that you have observed till now. Where? Well, 223 hours. So like a lifetime of 225 bulbs. So 200 in number. Here you have also studied that there are 30 independent measurements measured. So n is equal to almost 30. So 10 compared to that is kind of low. So usually 10 or less, I would say it is an interesting observation. Again, this is not hardcore truth, but it's a type of normal distribution where smaller sample sizes will be involved in it. And of course, the variance has to be unknown. If the variance is known, then this has to be the t distribution. I'm sorry, z distribution. But then the variance is unknown. Also adds up to the fact that these are, 10 or lower, very like sample space is very less. Just an interesting observation. Okay, so how do you do that though? So remember, like, first of all, you have to find out the value of alpha, right? So once you find out the value of alpha, what do you do with it? You put it into the, so what is step one? Step one is to identify that this is a t distribution. Once you have identified that this is a t distribution, what do? You find out, well, n is equal to 10. So remember the data collection steps that we have, right? So n is equal to 10. Where's my mouse? Okay. X of n. Now this is, I'm using the book notation so that you can follow the book very closely. You need not like write it like this, okay? But 70, okay, wait, 57.3 sample variance, okay? So sigma n, actually sigma n squared, sigma n is the standard deviation. That's given as 23.2. And then you already have the t distribution. So you can either start with the t distribution as your conclusion in the first, or you can actually write it, since this is an unknown variance, we have t distribution, but you have to write it because this is unknown. Unknown what? Unknown variance. Okay, so that is supposed to be known. Okay, then what do? Well, then you have already concluded that. So then 90% means what? Well, 90% means it's 1 minus 0.0, 0.90 basically. So this is basically it comes out to 0.05, but I have to just show everything. So my alpha by 2 is basically 0.05, right? So then what we have is t of alpha by 2, right? I'm sorry, t of alpha. I always make this mistake. And it's funny that I never change it year after year. So t of alpha is basically your what? So you have to now actually see your t table. So if you see your t tables, let's see if I can actually see my t table. Okay. Could be somewhere given out here. Anyway, even if I don't find it or find it, we are not going to waste too much of time looking at the, oh, never mind, we found it. Okay, so the value of, again, n is given out here. The value of alpha is given out here. Why is that important? Well, if you see the structure of how the t distribution is, you will actually see that t of alpha by 2 and n. Now z of alpha by 2. So there is no n part in it, okay? T is basically having an n part. So alpha by 2 and n. So alpha by 2 is 0.05. And what is the n? N is 10. N minus 1 is what? N minus 1 is 10 minus 1, which is 9. So then you go back to your thing. You say, okay, let me see, 0.5, and then it's 9. So it's somewhere this value. Okay, so that's how you find out. And why am I showing this to you? Well, you already know this probably by now. But anyway, I mean, I'm just trying to show it because some people might have like confusion about how to actually get about looking at the table. Okay, so let's get back to our business. So if you see the value, it will be 1. Oh God, now I forgot. Okay, 1.833. Now again, 1.83 is also fine. Okay, so don't worry about it. 1.83. Let's write 83. Similarly, then you put it into the interval. I'm not just calculating that. Then you take this and you put it into the CI. Where do you find the CI value? Well, you use this t distribution table out here. That is xn minus t of alpha by 2 n minus 1. You already found that out. And then you have sigma divided by n square root of n. Okay. And then xn plus this. So xn minus this and xn plus this. So it's similar to the chi distribution table out here. Okay. So I'm kind of like trying to avoid that part. Again, if you cannot work it out, you can come to me and I'll show you how to basically work it out. So again, like this will be 57.3 minus 1.833 that you have already found out, and into the square root of, what is the variance? 23.2 divided by, so basically you get the point, right? I mean, this is just repetition of, okay, now I forgot what I have to, okay, I think it's square root of 10. Let me just check. Yeah, it's square root of 10, okay? And then the other part will be give a comma out here, and the other part will be basically 57.3 plus the exact same value, okay? Plus the exact same thing that you have out here, okay? So these are your intervals. So again, as you practice, if you're practicing it with me, you'll find out that as you find the data, the first thing is the distribution, then is the collection of the data, then is finding the value of alpha, then is putting it into the confidence interval formula, and just crunching the numbers in your calculator and finding out what is the different confidence interval. It shouldn't even take you much longer time. Just be careful that you are selecting your distributions correctly. Okay. All right. That's all you have. This is just part A. There is, in your homework solutions, you might have part B and part C having different types of distributions. So just be careful of that. Okay, so having said that, now we move on to a little bit of complicated problems. So usually if you see your solution, now this is your solution for the entire homework 6, right? So let's yeah. Your entire homework 6, you have these kind of problems. Now, the first part of the homework 6 is a bit complicated, okay? So we are going to try and not repeat too many complicated problems. Like if you find out like fx of y has a distributions, and then we are trying to find out marginal densities and stuff like that. We are trying not to repeat the same problems again, but then you should be knowing, since homework number 6 is a part of your exam solution, your final exams, the scope is the same. So you should be able to do these problems if in case it comes in. Now the problems like this one, where there is a conditional probability involved, you might not get these problems because this is almost like Bayes rule type of problem going on out here. But for those of you who are taking up communications, telecom courses, I hope some of you do. If you are, then you will be required to know these kind of communication problems, because this problem is a binary communication channel where you have noise introduced, and then we are trying to find out if the 1 is sent, and if y is greater than is equal to 0, then what kind of probability do we have for this particular distribution. This is also very important for those of you who are taking up digital communications in the future. These type of problems will be coming back to you. So just a heads up. Well, let's see. Again, we are trying not to repeat the same things that we have. So basically, this is your marginal stuff. We are going to try and not repeat that again. Somebody asked me, why are they independent? Because they can be separated out into two random variables like this one. I think, David, you asked me why they are independent. So yeah, they can be separated out into two parts. That's why they are independent of each other. So this is a little bit complicated math problem. So this might actually take you a little bit of time to solve in the exam hall, especially if you give some problems like this in the exam hall, you might be a little bit wary. So we are going to try and not make your exam difficult. But at the same time, you can expect something like a problem, again, going back to Canvas, problem 5.26, 5.31, 5.35. So these are basically problems of your standard, like if you go to your book, let's go down to our chapter 5. You will see that most of you already know most of it. So let's see, since our professor has mentioned these problems, you don't need to actually go through these problems. You can actually go through your homework and then find out that these problems are almost similar. Mostly they are already solved by you. So problems like 6.26, like finding the value of k and then finding these type of problems you have already done in the homework, right? So, I mean, I'm trying to actually go according to professor as well. So 5.35, 5.43, these type of problems are a little bit on the complicated side, but not too much complicated again. So, oops. If the problems are independent or not, yes, we are going to solve problems. The last problem that we have right now, we are going to actually solve the problems of independency and what is orthogonal, what is independent, and what is non-correlated. So again, I'm going to refresh your memory and I'm going to kind of round up the course, trying to kind of relate the last few chapters with the first few chapters that we have learned, and give you a summary of why we are looking for independence or uncorrelated or whatever. So these are those kinds of problems. Again, going back, 5.48, 5.50, let's check those. Like 5.48, you have done like the value kind of problem. 5.50 is again independence, all those stuff. And then of course you are going to have, okay, so these problems 68, 95, 105, these are like more, I mean, they're more of like joint moments and correlation and covariance kind of problems. So you are and you will be given to find out, like find the correlation and covariance of X and Y. How do you find that out? Well, it's pretty straightforward, just your formula basically. So if you study the functions of two random variables, you're going to actually, again, whatever you have, you're going to be able to find out. All the formula will be given at the back of your exam. So I'm just going through it because they might or might not be important for your exams perspective. This is basically Jacobian. Again, Jacobian, if we give anything, I'm going to send you a kind of PDF practice problems and the solutions. So don't worry about that. So there's a beautiful problem on Jacobian. Jacobian is also important. It's a very good linear transformation problem. From the perspective of those of you who are going to take up a little bit of math heavy courses in the future, Jacobian is something that you should be able to know. So the covariance formula is pretty much given to you. And again, like the bigger formula is basically your correlation coefficient, and your correlation coefficient will be practically given to you. So this is again a very complicated problem, but a very good problem for you to understand the concepts of what is basically, again, for those of you who are taking up signal processing on any kind of signal processing classes in the future. I know there are many, many fast track master's program candidates in the future. So for those people, estimation of signal and noise is very important for you. Just look through it. It's again a very simple concept. It looks very mathematically heavy. It's just Gaussian. And the correlation coefficient formula is given to you. So if you have a problem which has a correlation coefficient formula in your homework, you should concentrate on that. Let me see if there is any. Yes, so problem 5.65 might be important to you because you have to find out, excuse me. So you have to find out the E of X. So this is the expected value. Okay. Now, after finding out the expected value, you are also trying to calculate the variance. And then you're trying to find out the distribution, collective distribution. Now, this type of problem might be very important for your exams perspective. And then once you try to find out so this is just plain integration, as you can see. Like, I mean, if I can definitely solve this for you, but this is just you remembering that if it's E of X squared, you just kind of square these equations together. If it's E of X, you just take E of X. And yep. So basically your covariance is E of xy minus E of X into E of Y. This formula will be given at the back of your exam. And you just have to put in the numbers to find it out. Now we are going to talk about independence and correlated data, but this particular problem might be important from your exam's perspective. 5.65. Okay. Now let me see any other problems that can be there. This is again the same thing that we have done in the past as well. Finding the region of interest and then trying to, so we are not going to try and give you like too many complicated region of interests. But it's good to have, like, as a problem session. Let me see. Yeah, I think 5.65 could be a great example for us about trying to find out the correlation, the expected value, and then finally the variance of the problem. Yeah. You might also be told to find out the correlation coefficient. If you are told, the formula will be given at the back of your book. But if you already have the covariance and if you already have the variance, you should be, so variance is out here, var of y and var of x. You should be able to put this in the formula, right? So where is the formula? Well, the formula will again be given to you at the back of your exam, but you have to remember the formula. I mean, remember in the sense that what to put where. That's all. So don't be afraid that, oh, we haven't done anything, any problems on that. How are we going to even find out the correlation coefficient? This is impossible. No, it's not. Actually, the formula itself is very, very simple. And I'm kind of getting irritated on why it's taking me so long time to actually reach there. Anyway, somewhere. Let's see. Anyway, it will be given to, it might or might not come in. But if you have the covariance, it's the covariance divided by the standard deviations of the both. And you also have kind of touched based on your correlation coefficients for your project as well. So for project 2, you are trying to, okay, so project 2, it's a good time for me to actually talk about project 2 though. There are a few submissions for project 2, but then I have been asked multiple times that, okay, what are we even finding out? So the basis of the correlation is that the covariance kind of, and actually I can turn on my video right now. So let me do that. The correlation kind of gives you okay, so let's talk about covariance first. The covariance kind of, first of all, gives you the number, and there might or might not be a magnitude associated with it. But when you do corref for your project or correlation coefficient, when you're trying to find out the correlation coefficient, point 1 is that you're trying to find out the correlation coefficient for the entire matrix. Okay. Now, once you find that out, what you're trying to do is you're trying to compare each pixels together, right? So each of these pixels are pixel 1, pixel 2 compared, pixel 2, pixel 3 compared, pixel 3, pixel 4 compared, right? So this is a matrix of numbers like that. So now, when you have pixels of numbers, correlation coefficient is just a value for your, if you get that problem in your final exam, it will be just a number. But for your project's sake, I'm explaining you that this is a bunch of values in a matrix. Now, how do you interpret it? There is a positive direction for correlation. There is a negative direction for correlation. So some of the values you will find out will be positive values. Some of the values may be 0, okay? And some of the values may be negative. So correlation not only gives you the magnitude of how much it is correlated with each other, it also gives you the direction in which it's correlated. So negative value is like it's not correlated at all. Zero means it's, well, uncorrelated. And positive direction is that, so there are shades of grays and shades of total whites, right? So they might be like somewhat correlated, but there are shades of black and then shades of white, totally like uncorrelated data. So it gives you kind of the direction in which your correlation kind of exists. So it's almost like a vector. You have the magnitude and you also have the direction of it. And you can treat covariance as just a scalar with just the magnitude. Okay, very wrong analogy, but that's the picture that you can draw in your head. Not a part of your final exam, but just explaining it. Anyway, so now we have a problem, right? This problem is already given to you in your homework 6. So problem 5.62, 5.65, these are the problems that you will expect to find out, or expect for you to be solving types of problems like that. Might not be the exact problem. So here you have like n as the number of web page requests arriving at a server. And those web page requests have this p and 1 minus p kind of structure. So even if it looks like a Poisson's random variable, yes, you can solve this by Poisson's random variable. Okay. For those of you who are extremely uncomfortable taking time periods and not thinking that this is Poisson, you can do a Poisson. The point is not how you solve the random variable. The point is whether you can separate these two random variables out. What do I mean by that? We'll find out. So p and 1 minus p, this has been approximated as binomial. Don't come attacking me. Yes, you can do this by Poissons as well. Okay, that's the answer. So now, what are we told to find out? So there is a web page requests that come in at certain intervals. And you have to assume that this first page is N1, the second page comes in at N2. And so if you have that kind of problem, you're trying to find out the correlation and covariance of N1 and N2. And then you're trying to find out whether these type of random variables are independent, orthogonal, or uncorrelated. Now, why is this important? Now, well, again, I am from the communication sector, so I can give you great examples in communication field, but I'm pretty sure that somebody from control systems can also give you great examples in controls as well. But more from the communication perspective, the noise, if we do not treat this as an independent entity, kind of independent from the signal, although in real world, it might be a little bit difficult for us to kind of identify, oh, this is noise and this is the signal, but we treat them as independent entities sometimes. So it's very important for us to understand whether that certain type of random variables that we are getting in sequence, whether they are kind of related to each other, how much are they related to each other? Okay, they are absolutely not related to each other. Are they orthogonal to each other? So these information, it's actually a privilege for us to find out this type of information, because we do a lot of processing to actually get to the point where we can actually deduce these kind of information from the signal. Okay, because imagine that you are getting like a speech signal, like I probably have shown you several times. How are you going to approximate that type of signal? If you cannot approximate that type of signal, you won't be knowing what type of architecture you require to actually receive that signal, to actually process that signal so that we can hear you. You can see me and hear me because of a certain technology, right? So they're important, So now what we are having is N1 and N2. That's all we have. So N1 and N2, what kind of random variable is that? You can use Poissons. I have used binomial out here because it's 1 minus P and P kind of architecture. You already have 100 milliseconds, sorry, not micro, milliseconds period, and N2 is a web page having similar period. So now we are assuming an interval of 1, and one of the page takes a probability of 1 minus P and P. And what we are trying to find out is N1 and N2. So I have approximated N1 as a binomial random variable. You can do it Poissons. And N2 is also another binomial random variable. So this is binomial random variable number 1. This is binomial random variable number 2. So that's how my P of N1, N2 looks like. Now, what is this though? So remember how I write P of X and X? So since we are trying to find out N1 and N2 together, that's why I've written like this. P of N1, N2, small n, these are just numbers, okay? Just like the brace out here, this is just a number. So this is how you write probability. So yeah. So we are trying to find out the correlation. So before that, we have to find out what type of random variable it is so that we find out the correlation. So now we are trying to find out the expected value of that. So what is that though? We already have the distribution. We just have to sum it up from 0 to 100. Why? Because, well, assuming that it starts from 0. Again, this will not be given to you. You have to I cannot assume negative numbers for Poisson's or binomial random variable on a real number line. So I have to start from 0. So from 0 to 100, we are trying to find out the expected value of the mean. Why? Well, that's the first step for me to actually find out whether they are correlated or not, right? So we put in the formulas and then we see, well, these are summations, right? So we can separate them out and we can write summation of n is equal to, or rather n1 is equal to 0 to 100. And then we can take this out, right? So we have 100. Suppose n1 represents the capital N1. And then you have 0.05 to the power of N1 and 1 minus 0.05, which is basically 0.95 to the power of 100 minus 1. Okay, so 100 minus N1. So this one is a separate entity. Similarly, we can actually separate out. So I have taken this one, and this one. And then we are actually multiplying it with the number of N1s that we have. So then we have taken this one as well. So we have taken these 4 entities and separated out, and then we are left with N2, 1, 2, 3, and 4. So these are left out 1, 2, 3, and 4. So then we can actually write, okay, well, this is the expected value. Excuse me. These are the expected value. Now, somebody obviously will ask me, why did you multiply N1? Well, where's my mouse? Oh, there. Well, if you actually study the expected value formula, E of X. Now we have not done too many problems of E of X. That's why you might not be familiar with this. So Fx is the distribution. Okay. So that is this guy. This is the distribution. You also have to multiply the number, right? So it's Fx. So now this is the number N1. Where's my mouse? So this is the number N1 and this is the distribution. We are taking a sum of that. So hope it's clear. And why we are taking a summation and not taking an integration like I've stated in the formula out here? Well, because this is a discrete random variable. Even if you're taking it at Poisson's, it would if you're taking something in a continuous random scale, then yes. Otherwise, it's always a summation. So it depends on the type of approximation you're doing. I've taken binomial out here, you can take Poisson's. But be careful of the summation or integration depending on whether you're approximating it in discrete space or continuous space. This is a discrete space, that is why it's summation. Anyway, the point is that we can separate these two out, and hence E of N1, N2 is basically E of N1 multiplied by E of N2. How does that help us? Well, that helps us because the formula for the covariance is this. Now, this will be given at the back of. Now, I won't give you that this is equal to 0, but this will be given that covariance is basically E of N1, N2 minus E of N1 and E of N2. So the joint distribution or the expected value mean of the joint minus the individual expected values or individual means. Okay. So, well, the individual mean, whatever it may be, is basically exactly equal to the joint mean, so then the value is 0. That's great, but then how do you interpret this? This zero value is interpreted as they're independent and uncorrelated. Now, had this variance been a like it has to be zero for it to be orthogonal. Okay, so orthogonality also has like very good applications in something called basis functions. If again you take up digicom, or if you take up oh my gosh, not probability, you are in probability. If you take up telecom, you will be finding out something called basis function, something called I diagram. Then orthogonality will actually play a very important role there. So something like a covariance, if they are trying, so we'll find out covariance in a very interesting way. If some of you are there in that class, you will be trying to find out the inner product of something called the signal, and then there will be something called the basis function. It is represented like this. And then you will actually exactly try to find out whether they are correlated with each other or not. And if this correlation comes out to be zero, then they are orthogonal. And that's great news for us, because that kind of reduces the number of calculations that we have. That's great. But then it has another significance as well. This is not important. But what I'm trying to find out, I'm trying to give you like small hints on where we use these types of concepts. Okay, so let's erase that. Yeah, so now this is not equal to zero, so they are not orthogonal. It has a value. Why does it have a value? How do you know? Well, because n1 and n2 will be having certain values. It's not equal to zero. So as long as it's not equal to zero, this summation will be having some value. So we know that this is non-negative or not equal to zero. So it's not orthogonal. So orthogonality principle is what then? If the joint expected value comes out to be zero, then it's orthogonal. If it comes out to be some number which can be separated out into the individual means, then and only then it's independent. And of course they are uncorrelated, because well, if the covariance is zero, then it's pretty much uncorrelated. So that's some conclusion that we have from this specific final exam point. Now from here, you might also be given somehow to find out the rho. Now you should not be too much again surprised if you do get those problems, because it will be formula based. If you'll already be having the covariance values. Now this problem does not have it. That's why I kind of indicated that this problem kind of is a practical applications, because we do have the values for these problems. So once you find out the covariance, you already have the variance and the covariance, then you can actually find out the rho of xy small. Like rho is basically just a number, like, a number like minus 144 or whatever is given out here. So it will be just a number like that. Okay. So this problem, again, I have not put this into the presentation, but I'm telling you, problem number 5.65 or 5.65. Let's see. So yeah, 5.65 is similar to 5.68. Let's see actually what 5.68 is. I'm curious. Is it something that is very different? Let's see. Find the correlation coefficient. So this is the exact problem. Now we are going to actually solve this problem, and I'll show you exactly. I'm hoping I'll show you exactly where we have this type of correlation answers to that. But the point is that you do have sometimes the correlation kind of problems given out here. So 5.65. So I've mentioned, I think, this in the presentation as well, somewhere, I'm hoping. So I have mentioned practice problem 5.65 because that might be important. Now actually I can write and problem 5.68. So because 5.68 is the last problem that we have out here for our problem session right now, and it will be really difficult for me to find out the exact space in which we have the estimations. So please be patient with me. Is it the maximum likelihood, or am I like too way off? Might not. Let's see. Here's the grammar. I don't do very well with these online copies. Here somewhere. Actually, you know what? The Jacobian, now that I'm thinking, we might give you like a small problem. So you see, like when you have row of x, y, you just have the covariance and you have to just divide it with sigma 1 and sigma 2. So if you have the covariance of x, y, and if you have the variance of x and y, you just divide it. So I mean, I'm just saying as the problems are coming by, so that we are kind of covering everything that we have for the as we yeah, I mean, so the row of x, y is basically, this is the formula for it. So it will be given for your exam. It's just that once you find out, so for this example that you have 5.65, you have the variance of x and you have the variance of y. So this is 11 by 144, right? So all you need to do is whatever this horrible number is, 1 minus 1 divided by 144, you have to just divide it 2 times of, let's see, 2 times into 11 by 144, whatever that value is, right? That's all. I mean, that's why I'm not even like showing it to you. In case that comes in. I'm not saying that this is going to come in, but in case that comes in. I'm going to be very surprised if the estimation problem is before this. Anyway, I mean, even if I don't find out where the estimation problem exactly is, you should have done something similar to that in your class. Parameter estimation is again a very if you go to Dr. Mandry's I think he does parameter estimations in some of the statistical signal processing or maybe neural networks. So you'll be having parameter estimations there. So again, for those of you who are interested in it. So maximum likelihood is also very important for those of you who are going to take up Digicom later on. Maximum log likelihood or maximum likelihood will be something that you will be hearing much more frequently in his class, in Dr. Skizes' class, if you are interested. Let me see. I don't know where the estimation problem is. Do you know, guys? If I find out, I'll give you the page number for it. So basically,
I think it's in chapter 8.
8? Okay, yeah.
I'm pretty sure
I am
you're
actually
right
in
spot.
chapter 8, but then where is the question?
Let me look.
Let me look, because I don't do very well with the online copy and my book is somewhere. Let's see. Is it in the testing part? I don't think so. Testing is like totally different. Interesting. It's easier. I mean, I can actually talk about estimation until I actually find this out. So basically what we have as an estimation, testing is very important. Okay, so testing actually, the maximum log likelihood or the maximum ratio function, it kind of is very interesting because this always works with the entropy of the problem. Now, again, this is deeper into the communication, so this is not required for your exam. But since I came across this topic, I can actually talk a little bit about it. Testing, you'll not have anything from this chapter, okay? But just for your knowledge base, since we are wrapping up all our theory problems and everything else, so maximum log likelihood is, or maximum likelihood function is basically works on your entropy. Now, entropy, you had already had that problem in your exam, where we calculated the information content or the quality of the information content. Yeah, I don't know where it is exactly. I hate to take out my book right now, but the estimation problem, I'm not sure in the vectors we have that. But anyway, do we have that in the vectors? No, I don't think so. And you know what, like the funny part is that I keep on losing this every time and every batch. Like I never remember this ever. Anyway, I think I am in the right track. Let me see. Yes, I found it. Perfect. So this is your 6.5.2. This is called minimum MSE, or basically mean square error. Now you have different types of estimators. Okay, so first of all, what is an estimator? Now you might read this entire stuff from your book, and you will find out that, well, estimator is basically something that is trying to adjust its value or estimate its values, trying to find out the closest value as possible. Okay, so again, control systems will have feedback loops. Now, what is the point of the feedback loop? Now, if I give you 30 is your target speed, okay? And I give you like, okay, build a car, here are your equipments, and 30 is the speed. So you do a test run, okay? You have built all your components and you do a test run. And say you have like 20 as your speed for the first test run. Then you tweak something again. Then you run it again. 25, you reach this time 25 instead of 30. Then you again take the car back, you tweak it again, and then finally on the third run, you get 30. So this is exactly what your estimator is trying to do. You have a process, okay? Your equation is that y is equal to x cap is basically some g of y, right? So g of y means what? Well, your y is, or x, whichever you are trying to. So x is a given function, okay? So let me actually go back and forth. All right, let me take an F5 of this one, and I hope this works. How do I escape this? Never mind. All right. So how it works is basically you have you'll be given, first of all, x, okay? So x, and then you have x hat. So x hat is what we are finding out. So x is given as some linear combination. A is basically, I'm going to explain you in the terms of machine learning again, because that's what I know. You can actually do it in any other formats you want. Again, any variables will work, but I'm trying to be as precise as your book. So I'm going to try and take g of y kind of variable. So any kind of linear combinations, it's going to work. So if it might be a1 y1 plus a2 y2 plus b, any combinations are going to work. Okay. So this is in terms of ML, machine learning. These are called your weights. Okay. Let me write my E properly, and this is I, okay? These are called your weights, and these are basically called your bias, okay? Now, it will make sense when we start working on the problem. So then we have something called X cap. Now let's go back to our textbook, okay? So what it's trying to say is that we have now an X cap, which is basically an observation. So you have built a machine, okay? Now let's go into a machine analogy. You have built your machine, and you find out that, well, this might be, I've given you the speed as 30. So on your first run, you have 20. Okay, what are your adjustment parameters that you're going to take this feedback 20, you're going to make some tweaks and then come back and test it again. You're trying to reach a target. Your target might be 30. And what you are getting out here as an observation might be 20, 25, and then 30, right? So this is what your X hat really means, your observations. So then what you have is you're trying to find out the error, right? So this is important for us. So let's write that down. What we are trying to actually find out for each of the feedback is the error. So what are you tweaking basically? What are we trying to tweak? This is the value that we are actually interested in, right? We are trying to reach as close as possible to this value. And this is the X that we have. And then we are trying to tweak the parameters A and B in this X hat such that X hat becomes much more closer to X. But then how do we do that? We calculate the error. So that is X minus X hat, right? So this is the error that we have. Now, what does that mean though? I mean, then like, okay, great. But then we have like one set of errors and the other set of errors. So, well, this can be a positive value or this can be a negative value. So then instead of doing a mod, you can do a mod as well, but then mod maximizing and minimizing in terms of convex optimization and in terms of optimization, we actually avoid mod. Okay, mod means your modulus operator, which actually looks like this, right? So it kind of gets a little ugly. So we are taking square. So that is why this entire process is called minimum mean square error. Okay, so why is it minimum? We'll see in a while. So for now, we have mean square error. Why? Because we are kind of having, this is like a weighted mean, so this is like, y is your observations. We are kind of having a weighted mean of that. And then we are squaring that. So that is why it's called mean square error. Okay, so this is a random variable at hand. Okay, and this is also a random variable at hand. This is some linear combinations of A and B, which we have selected. And we are trying to adjust these two parameters such that the x cap that we have, these observations that we take each time, they are as closer as possible to x. Okay. Now, oops, sorry, back to our book. So now then what we do? We minimize it. Why do we minimize it? Well, the point is that we have to reach as close as possible by reducing the error. So what do you write in mathematical term in terms of error or E? So we minimize E. So we minimize E, but then minimization has to do with some parameters, right? What are you minimizing? Yeah, you are minimizing the error. Okay, if this is small e, which is your expected value, and then expected value means mean, right? By the way, so we have told that it's MSE. It's mean squared estimate. Okay, so mean squared error. So mean squared estimates. So E is that, great. But then what we do with E? We minimize E. Okay. With respect to what? So we are minimizing this. Great. We are trying to minimize the error. But then what do you do to minimize the error? So if you are trying to maximize your car speed, like I said in the given example that we had talked about earlier, what do? You go and let me see how much oil is it consuming, or let me see how much of, is there the different structure that we can take? What is the aerodynamics of the entire structure? Can we change that? So we are trying to minimize something in that error, in that gap that we have. So we are trying to build some structural changes, but in this equation that you have, the only parameters that you can work with is A and B, right? Because Y is a random variable. You cannot do anything with that, right? So now that is why in your book you have minimization of A. So you see these two values, minimization of A. So you're minimizing A. Well, then you follow, once you minimize the A with respect to your equations that is given, then you find out that you find an A star. Okay, so well, minimization of this, whatever the equation is. So we are going to give you something of X. So you minimize that with respect to A. So if you go back to your problem, X minus X hat is what? Well, it's AY plus B, right? So then if you have A, so if you're minimizing A, you are kind of, I'll give you the workout of this entire problem. I'm not working out because, again, for time's sake, because we are almost up of time. But then you're basically taking D of DA, okay? And again, when you're differentiating with respect to B, you're taking D of DB. I'll give you the workout, don't worry about that. So the point is that you are kind of differentiating them, you're minimizing them, and you're trying to actually find out the minimization and equate this entire thing to 0, okay? And then trying to find out A star. So I'm just giving you a basic idea, and B star. This will look a little bit bizarre right now, but then I'm trying to give you an order in which we are trying to do the problem. So let's go back. So that's what you have in here. Okay, so A star is basically whatever you find out, and B star will be, again, you put in X minus AY minus B, and then you have that in squared terms. So you have to minimize that with respect to B. First, minimize that with respect to A, then put the A, whatever A star you have. So let me give a little bit background on here as well. So this is in optimization, in convex optimization. If you take up convex optimization classes later on, or optimization classes, this is called the optimal A. Okay. Again, not important. I'm just giving you an overall basis. Okay. This is called the optimal values. Okay. So once you differentiate and find out for one parameter, what you do is you go back and substitute that. Okay. So your step one, whatever you do out here, I'll give you what you have to exactly do. So then once you find that out, you have to go back and substitute it. Okay. So now it's A star Y plus B. Then you again differentiate it with respect to B. So that's exactly what they have done though. They have taken and they have substituted the A star, and then they have proceeded in going about and finding the B star. So once you find out both the A star and the B star, you basically they are trying to even like find out, once we differentiate it with respect to A and then try to find out A. So this process keeps on repeating. And then you come up with the next set of A stars and next set of B stars again. So then basically it kind of arranges itself in a nice, neat formula that you have out here. So basically that kind of is the, like, you see that this is the correlation coefficient, and then you can actually, I mean, this is just a covariance. I mean, the covariance can be written like this, and then you have the variance of y, so that cancels out, and then you can write the final formula as this. This does not mean anything, right? I mean, this is just a fancy way of writing it, A star. But then what you do is you actually substitute it, like out here. You have to substitute these values in the entire equation x. So what you have out here is basically, once you find out A star and B star, you have to put it back into this x star. So, oh, sorry, x hat. So then again, you have in the next cycle, you find out E dashed. What is E dashed out here? This is again the expected value of the error between this one minus whatever is this out here. You continue doing that until this expected value or the error function is almost equivalent to 0. I mean, it's never equivalent to 0, but we are trying to find out the first, I mean, this is like, this is, well, this is ridiculous for me to write, but anyway, we are trying to find out the, you know, some estimators do really well in going like 0.0000 something. So that's what we are trying to do though. So your book in this example is what it's trying to do is, first of all, have an equation. This is the error function that you have, and then trying to find out the optimal value of A, optimal value of B, and then substitute it in that equation, trying to find out the another set of optimal values of A and optimal values of B, then again substituting it back, and then trying to find out, well, we have X hat, and then after the X hat, what can we do? Is it like, what are the types of characteristics do you have? And it keeps on repeating until whatever your error margin is, it's reached. But you don't have to repeat that 1,000 times. You just have to know how to solve this particular part out. And I think I have a very good example for that. I think we did it with 3 random variables. You don't have to do it with 3 random variables, but just look through the document in how we have, like how we do it step by step by step. Let me see if I have that document with me. Yeah, I do not know where I have that document, so I'm going to share it with you just for you to see what type of steps you have. But mostly I am hoping that this will be the problem given to you. This is y, and then you have to find x minus x hat, and then you have to find out A, you have to find out B. These are your optimal A and B, and then you have to find out your x hat. I mean, I am pretty sure that professor has shown you how to do that, but I am also going to share you a separate document so that you have an idea of what type of processing goes on in this feedback, so that slowly, like if you have like a baseline curve in machine learning, you will slowly see it kind of trying to fit. So when you hear the word trying to fit the curve, that's what it's trying to do. And you have different types of gradient problems that you kind of trying to solve. You have just gradient, and then you have conjugate gradients. And so when you say gradient, what you're trying to solve is DDA or DDB, or trying to kind of differentiate with respect to some parameters called weight, differentiate with biases, and then trying to substitute the new weights and biases into the equation so that it slowly kind of fits into the curve. And each iteration, you will actually try more and more to fit in according to the original curve that you have. Okay. So these type of problems, that is why the baseline for this type of problem is important for us. That's why it's given for you in the final exam. So I think that's the scope of your entire final exam. I'm going to actually say, yes, please keep it. Yeah, I'm going to actually try and save these, whatever I have, and share it with you immediately, along with that threefold kind of, I don't remember, it's a very long time ago that I have actually solved this, and so it's been a while that I have shared it with any batch of students. So I have to actually see where that file is, but it's actually a linear estimator problem similar to this one. And you will see how I've tried to calculate the A star, the B star, and then put it back in the problem. It's a very messy, big chunk. You don't have to do it with 3 variables. You can try it with 2. And if you have any problems, any questions, come back and ask me on Teams.
Aileen,
Yes.
I do have a question, but it's on project 2. Because I've been stuck on step 3 for a while now.
3? Okay, yeah,
yeah,
you can
step
ask.
3.
I mean, if you want to, I mean, I'm
Yes.
done with my problems.
Yeah,
Okay, so let's open that. I mean, I don't remember what I've said.
yeah, I know you went over a little bit about the project 2.
Okay.
So for step 3, I know you said you wanted to store the difference between the adjacent pixel values. So for this step, I did like a little bit of research on it myself, and I find that it was recommended to use convolution function, or was it a different function for that?
You do have a function for that, but then you need to understand how to use it. I mean, it's just a very simple one function statement.
Is it like an if statement, or?
It's not an if statement. There is something that you can directly use to find the difference of pixels. So if you find how to, just Google how to calculate difference of pixels in MATLAB, you should be able to get that specific function. Yeah.
Okay.
Yeah.
Yeah, because I tried convolution, but
I mean, convolution could be a great way. Actually,
right.
I mean, in machine learning terms, again, the one that I have, the big projects that I work into.
Yes.
So if you see, like, this is the image, we have something
Right.
called a filter. So our filter will go along the, like, filter, it depends on how big the filter is, like 5 by 5, 3 by 3. So it will actually convolve all the things in, and then again go and then convolve all the things. That's a way of doing it, but this is not what we are wanting out here. We are wanting, like, okay, if you have like one teeny tiny box minus another teeny tiny box. Okay, right. So yeah, you're right. I mean, I'm not saying that you are not right. I mean, if your convolution filter that you are doing, if your convolution filter is 1 by 1, then it's still not basically a difference of pixels. You know, it will convolve and give you a value that is basically a reduction of dimension, but it's not going to reduce the dimension because it's a 1 by 1 pixel. So it's not going to be exactly correct, but the way that you're thinking is correct. You know, we do use convolution in image processing. Yes, heavily. That's why it is called CNN, or convolutional neural networks. And I heavily work on that, but probably not out here.
Okay, so for this project, just for the sake of this project, you want us to use something else other than that to find the difference in pixels?
Yes. Yeah, we can take this discussion offline. I mean, we can do it like 101. You can like send me an email and I can help you with that. Yeah.
Okay.
Yeah.
Okay, I'll do that. Thank you.
Yeah. Any other
And I just
questions? Wait,
just a quick one. You said for the exam we should probably focus on homeworks 5, 6, and 7 primarily.
Let me see.
I just want to make sure that this.
Yeah. Let me actually.
Scope.
So homework 5 is what? Let me see. Yeah, I mean, don't focus too much on 5.7. Yeah, this should be enough. I mean, not even like 5, but I mean, just for the sake, because professor has given you the entire structure and he has kind of heavily included problems 4. But problem 4 is like basically your functions of one random variable. These problems are basically problems from functions of one random variable. So I would say not too much. Again, let me have a final discussion. These problems are basically, I'm pretty sure that it's unexpected values and stuff like that. But then I think it's much more important for us to cover the later part. So I would say if I were you, I would start revising from the confidence intervals because they are really easy. And then go into central limit theorem, go into this derivation. Okay, this derivation will come. I mean, I'm pretty sure that this is going to be one of the questions, if not of major denomination, but it will be like maybe at 15 or 10 points. So this one will be there. And I'll share the documents with you. Then go on to your functions of 2 random variables and try to find out your expected value, covariance, correlation. So you should be comfortable with using these terms correlation. Okay, what is correlation? It's covariance divided by sigma x, sigma y. Okay, let me try and find out. Okay, Aileen said problem 5.65. Let me try and find out the correlation coefficient of that. So those types. And then if you have time, go back and then try revising anything beyond like homework 5, 6, and 7. Yeah.
Okay. Sounds good. Thank you so much.
Yeah. So yeah, I mean, homework 4, it's like too much into your midterms, and homework 5 is actually technically your midterm. But then, yeah, homework 6 and 7 should be much more stressed on. I mean, if you have, since it's the finals, if you have time, you go through the homework 4, but I would say 5, 6, and 7 should be enough for you to get a very good score. Yeah.
Thank you.
Yeah. Any other questions before we drop? This is thankfully recorded. Thank you for the suggestion. And I will be uploading this to YouTube, and I'll be sharing that link with you after some time. You know, it takes a little bit time for us to upload things on YouTube. And then we are going to share the link, and now you'll have access. Everybody else will have access. Yep. Any other problems, any other questions, you can always come back and talk to me. So take care. Best of luck for your exams. I'm pretty sure you're going to do well.
Okay, take care. Bye.
Thank you. Bye-bye.